All right, so my name is Christian Engelmann from Oak Ridge National Laboratory, and I'm going to talk about characterizing faults, errors, and failures in extreme-scale computing systems. This is a joint project between Oak Ridge, Argonne National Laboratory, and Lawrence Livermore National Laboratory, and I am the principal investigator of this project. So what's our motivation here? Resilience in extreme-scale systems is technically an optimization problem between the key system design parameters, performance, resilience, and power consumption. Oftentimes, when we talk about resilience, we are basically saying, oh, the sky is falling, the sky is falling. Systems will be failing all over the place and things like that. That's not exactly the case. The case is that we basically have to deal with, every time we run into problems with our resilience, we need to compensate for that. We need to compensate in terms of adding maybe more hardware or dealing differently with it in software. And that may actually cost more money to do that, more power, or just takes longer to do, so it actually costs performance. So it's actually an optimization problem. And the challenge here is to basically build a reliable system within a certain given cost budget. After all, we won't be given billions of dollars to basically build an exascale system or post-exascale system. This requires us to fully understand what's going on in these systems in terms of what is the fault model, what is the impact of faults on applications, and how can we mitigate against hardware and software errors, and how can hardware and software help in this. So the objectives of this particular project is to identify, categorize, and model the faults, errors, and failures in HPC systems within the US Department of Energy, and to develop a fault taxonomy, a catalog, and models that capture the observed conditions and then also the inferred conditions in current systems, and then extrapolate that knowledge to exascale systems and beyond. This project basically provides a clear picture of the fault characteristics in current DOE computing environments. It improves resilience through a reliable fault detection at an early stage and actionable information for efficient mitigation. So the way this project works is actually, initially we started working on sort of offline analysis, looking at the data that we're getting from the systems, analyzing the data, categorizing the data, creating a fault catalog and models. Then we started looking at application sensitivity and studies and error propagation studies, doing application models, and feeding that back into the catalog. Right now, we're in the stage of online fault detection and categorization, where we look at live data from the system and try to identify the health of the system in real time. And all of this is done while refining instrumentation points, while we're trying to figure out what information do we actually need from the system, what information we can just throw away. So in the beginning of this project, about 3 years ago, we started developing a HPC fault taxonomy. This is already based on earlier work. There has been a significant amount of work at other labs. There was a workshop organized by Mark Sneer a few years ago, where we basically sat down for a week to discuss an HPC fault taxonomy. And based on that, we came up with a common set of terms, metrics, and methods. And I just made that more clarified that a little bit more, and basically came up with all these different terms. And for example, a fault, right? A fault is typically the root cause. It's not necessarily something you actually see. That's the problem we're often facing, that faults we often can't see. They can be benign, dominant, they can be active, things like that. And a fault then at some point produces an error. An error is typically something we see, and we may not see it. There's maybe detected and undetected errors, right? There may be mask errors. There are hard and soft errors. And then there, of course, is the failure. Failure is actually when a service fails, or when, for instance, when you have a library and at that library interface, a certain function doesn't work anymore, right? That's clearly a failure. And there we have also detected and undetected and permanent and transit and so on. And of course, the worst case scenario are the years. So when we developed this fault taxonomy, we started looking at the various different systems we have at these 3 labs, and started analyzing these systems in terms of what information do we see in the system logs and what can we make out of that? So at Oak Ridge, we analyzed 5 different generations of supercomputers over a period of 8 years, which is a total of something like 1.2 billion node hours of system logs. We combined this information from different system logs, and we started using standard methods, and we also created new methods for temporal and spatial analysis of errors and failures in these systems. And sort of we analyzed the correlation between different failure types, and we also compared the mean time between failures of these 5 systems. And something interesting to see here is that the mean time between failure here is normalized on a per node basis, basically. It's scale normalized. And we can see that the mean time between failure actually sometimes jumps rather drastically, basically on almost all systems except for this one. And this is something that actually was relatively new. We didn't expect that to happen, that even over time systems become more unreliable. And initially we thought maybe this is sort of a bathtub curve thing, that the system is becoming unreliable because it's becoming old. But here, this system isn't really old. And here, this system isn't really old either. So this is something completely different. This is typically changes in the system itself, where we updated maybe the software, or changes in how we use the system. Maybe we run applications that actually run the system more stressful, and therefore cause more errors. All these different types of errors and failures we're seeing in different percentiles of their contribution to the overall failures. And we can see that between different systems, sometimes there are similarities, but oftentimes they are not. We see on different systems also different errors and failures, despite the fact that all of these systems here are actually all Cray systems. They all come from the same vendor with a similar software stack, just the next generation. They all have the next generation hardware from the previous generation. And we always see that things like ECC errors, ECC double bit errors and things like that, yeah, they're there, but oftentimes we have network errors, and network errors are very typical to that particular network generation, because oftentimes we just report them back to the vendor, and the vendor then fixes that in the next generation. But then the next generation, then we see different network errors, right? So in one particular network, we may see drop packets. And the next one, we don't see that anymore. But we may see some node lockups that suddenly disable routes, network routes, right? So then we started looking at, okay, how is the mean time between failure distributed? And also how are the failures distributed, and how is that distribution related to the mean time between failures? And up here we can see that the red one is the mean time between failures, and the failures are nowhere near that, right? So the mean time between failures is, yeah, just that mean. The distribution is much, much different, right? So, and the spatial distribution sometimes really looks odd. We sometimes see correlation between heat and, so Titan was the first system where we actually saw a correlation between heat and failures. Previous systems did not have that at all. And in terms of mapping the failure distributions to actual the statistical distributions, we can see that Weibull actually matches typically pretty well. So we learned a lot of lessons from this. I don't have to go through all of these. The most important one is actually that mean time between failures average over time is not a very good measure for reliability. We need to come up with something different, something more parameterized, that is actually taking into account the current state of the system, which actually changes over time quite drastically. There are a lot of lessons learned with regards to temporal locality and spatial locality and things like that, but I don't necessarily have to go through all of these individually. We did a similar analysis with the Argonne Argonne Leadership Computing Facility at Argonne National Lab. With a mirror system there, we split between different faults, errors, and failures there, did a similar analysis, and came to some of the similar results, but also some different results. So for instance, mirror observed a higher failure rate during summertime than during wintertime, which we didn't see at Oak Ridge, and we still don't know exactly why that is. right? So at Livermore, one problem there is most of the big systems at Livermore, of course, are classified, and we can't really take that data and then just make that public. But we started working at Livermore, looking at clusters and looking at the memory errors, how the memory errors are distributed, and is the distribution actually matching up with anything else. So we do see a spatial correlation of memory errors, and we are still looking at, is that related to room temperature or is that related to something else? Something important to note here is that for all of these systems, especially less with a mirror system at Argonne, but especially with the Oak Ridge systems, when we do see a higher memory error rate, the first mitigation we do is actually swap that memory DIMM out with another compute node to make sure that we identify that the DIMM is actually the problem and not the compute node. It's a very good measure to basically over time weed out all the bad DIMMs and replace them and so on. But that requires us to track DIMMs, right? So because we want to actually have the error frequencies and fault modes of that particular component, not of the location, right? So that's sort of important to track components. A little bit about the tools. The initial analysis at Oak Ridge was pretty much done using just scripts. And within another project where we analyzed memory errors at Oak Ridge, we realized this is not really a very good way to do this. That other project basically where we ran the entire Titan memory errors through a script to analyze and bin the different types of faults, errors, and failures we're seeing, that script ran 8 to 9 hours. And after those 8 to 9 hours, we figured, oh, there was an error in the script. Okay, let's run it again, right? So this is not a very good idea to do research, right? So we started before that already developing different types of analysis software, and I'm going through a little bit of these. So this is Raven. This is actually our oldest tool that existed already something like almost 10 years ago, which was actually originally developed for Jaguar, I think, for the last Jaguar system, and then adapted to the Titan system. It basically has sort of a front end where you can click and select nodes, you can select time intervals, and then you can select event types, and you can visually inspect. Basically, you can figure out are there any sort of correlations, right? So here you can see a little bit. I'm just tracking my time here. How this works. So you basically have sort of here you see the event occurrences. Here you see how applications are basically allocated. And then you can do some analysis, some histograms and things like that. All nice and interesting to do. The problem is this doesn't scale, right? So realize we may operate here on several terabytes of data, right? So and this doesn't work. And so we started within this project developing different tools and things like that. So this was Loggator, developed at Argonne National Lab, which basically looked at the logs and started doing statistical analysis over the logs a little bit more in a more efficient way, doing spatial correlation, for instance, but also temporal correlation. The next one, also from Argonne National Lab, was also a visual tool. Was sort of the next generation visual tool, where again we had sort of an interface where we could select nodes, events, also applications, and then looked at what's going on in the system, and those arches here are actually autocorrelated events, where basically the system in the background is actually correlating our events and showing them. This is already sort of a first attempt in trying to basically automatically do something in the background. And then, so there's a little bit of a blow up of this picture. And then we started looking at, as I said, we did analysis of applications, how they behave. And at Lawrence Livermore National Lab, we basically developed this refine tool, which is a fault injection tool, which allows us to inject faults into applications, but into the backend code. Most fault injection tools either inject them right here in the intermediate representation or in the machine code. And the machine code is typically at the runtime using PIN. And the problem here is that we saw when we injected failures into the intermediate representation, it was the compiler actually optimized those faults away. So we actually didn't inject failures. They were optimized away. So this is actually the most accurate and the fastest way to actually inject failures into an application. And Lawrence Livermore National Lab, they're actually currently working on identifying different computational patterns within applications and then associating reliability characteristics to these application patterns, basically. And that's actually quite substantial work what they're doing over there. And now at Oak Ridge, I do have a little bit more time to talk about that. What we're doing is looking at the online analysis, and when we started looking at that, we realized that we did the offline analysis already in a way that doesn't facilitate the online analysis. So we had to start almost from scratch again, and we started looking at big data, right? Big data analytics, because at the end we're basically created our own analytics problem here. And we basically set up a system at Oak Ridge where we used an internal cloud infrastructure at Oak Ridge to deploy Apache Cassandra, Apache Spark, and basically ingest the system logs into the Cassandra database, already pre-processed, the events into a database, into database tables. The tables are organized sometimes by location, sometimes by event. There's always time series. And then we basically use Spark to do analytics over this database, basically. And using then, for instance, the Jupyter Notebook as sort of some type of front end, we can actually do very good analytics using this type of framework. And this surprised us a little bit that this works so well. We started doing machine learning over the failure data. We are starting doing pretty advanced statistics. We started doing principal component analysis, looking at information entropy. So trying to, for instance, figure out, okay, what information is in this system log? How does this information change over time? What information is actually essential here? And what information provides us indicators for the health of the system? So we just finished up a paper and submitted it on Sunday, where we basically came up with sort of a new way to analyze system health by just finding a simple indicator, a statistical indicator, that basically tells us something is wrong with the system. Now, what is wrong with the system then is still up to a separate analysis. But having already an indicator that tells us something is wrong on the system, and you add a live indicator, it's actually very interesting. So this is actually how we do this offline. Now, how do we do this online? Online, we basically ingest the data directly via a Kafka and Spark Streaming into the database, and Spark Streaming already does some analysis, and then publishes the event again, triggers other analysis, maybe it triggers users, maybe it triggers system operators, to basically then do more analytics over the data that's coming in, right? And that's what we're currently working on. It's actually a relatively large team that's currently working on this, looking at all kinds of interesting aspects to it. What I want out of this is, for instance, a notification about ongoing system health crisis. We are already there with that, with the paper we just submitted. And the more difficult one is a notification about root causes of application boards. So that we basically have then an online system where the application programmer who just ran a job and the job failed, he can go to that system and just give, that job ID, and gets a return back that basically says, your job failed because of this. This would be a great system. But we're still quite far away from that, right? Another interesting aspect would be just give the job ID and the system tells you back nothing was wrong with your job run, or your application is at fault, right? So that's something interesting as well. So with that, I'm just summarizing a little bit what we have done so far. We have identified, categorized, and modeled the fault, error, and failure properties of Department of Energy supercomputers. We have created a fault taxonomy, a catalog, and models of the conditions in current systems. We have developed a number of tools and frameworks for this. There are tons of publications out of here. We have 2 DSN publications just last week, 2 SC17 publications, a mascots, a DSN 17 paper, CC Grid 17 paper, and a few workshop papers, and then also an IPDPS paper in 2016. We are still in the process of actually publishing way more results. Unfortunately, some of our supercomputing papers got rejected. And as I said, ongoing work focused on the error propagation studies with applications, doing the patterns basically, the online analysis framework at models, and then the refinement of instrumentation points, which is also important. Because at the end, this logs mostly contain debug logs. It's mostly debugging. So what is interesting and necessary and what is not? What else do we need to add to that? So with that, I'm closing up, and if you have any questions. See, oh, yeah. There was a question up there.
Yeah. Thank you for this wonderful talk. This is actually an impressive amount of work. Maybe we can have some questions. I think you can press the mic button.
You start off by saying you showed a chart of mean time between failure. And it showed, I think, systems getting more reliable over time. Anyway, I'm curious if you have any anecdotal information from your user communities on these big machines as to soft failures. So the ones that are more insidious and supposedly going to happen more frequently on the new platforms. And I'm curious if you see any trend on the newer platforms with soft failures.
Yeah, so to correct you, so you mean soft errors, right? So, and you mean data corruption more precisely, yes. So yes, we have seen that. In fact, at Oak Ridge we had what was a system called GEA? Yeah, GEA system, which was actually doing climate and weather modeling. And during the last year of operation of that system, we ran some codes, and they were showing very odd data. And we realized after running some of the codes that there were some gaps in the system, and it took us, I think, several months to figure out that the processor was aging, and the guard bands inside the processor were just getting old, and we got bit flips within the logic of a processor. So that's, for instance, something that we did see at Oak Ridge directly.
Thank you. I have maybe just a small comment, because so you said the error were coming from the processor, not from the memory.
Yeah.
The memory was protected by ECC,
yeah.
I imagine? Okay.
Yeah.
I think you can press the mic button.
So I have two questions. I'll repeat James's question, which is, the MTBF charts you showed seem to show that the MTBF increased with time, which means the systems were getting more reliable, but you seem to imply that they were getting less reliable with time.
So there are a number of different jumps, right? And jumps are always bad, because we base our checkpoint intervals on the initial mean time between failures. So when you see the system getting more reliable, you're actually checkpointing for nothing. You're basically checkpointing way too frequent. That was one problem. And another problem was that sometimes we just saw drastic returns from basically it's jumping back to a lower mean time between failure, right? So that basically is something that we also didn't expect, right? So we saw both, basically systems becoming more reliable and systems becoming less reliable, right? And I'm mostly focused on becoming less reliable, because that's more of a concern than the more reliable. More reliable just means we are wasting more time on checkpointing. Less reliable means we're actually losing work. Right.
So as a follow-up question, at the very start you seem to imply that there was a phase where people were really worried about resilience, that the sky was going to fall, to paraphrase what you said. But you didn't think that that's necessarily the case, that the systems could be optimized to be more reliable. But at the same time, your studies show that we are far from understanding how systems face failure. So where is the gap there? Because if we don't even understand the resilience or reliability of systems, how can we be confident that they will be reliable?
Yeah, it's a very good question. So we understand some of it. And it's an ongoing struggle, not only of understanding, but also of a discussion with vendors, because we have also differences in opinion. So vendors will always tell us their system is reliable. And then we run them for 2-3 years and it's not. And then we look what is actually failing, and it's typically something that the vendor didn't expect. Right? So at one of the Jaguar systems we had, the Cray Jaguar systems, we had the problem that voltage regulators were blowing out. The voltage regulators were 5 times redundant. All 5 basically on a computer blew out one after another. The vendor never expected that. It's a $2 equipment that the voltage regulator, right? So basically a $10 failure basically resulted in a compute node outage. And on that particular network, a compute node outage meant that the router that's attached to the compute node was also going down. And since the vendor never expected that, the routing capability was static, which basically meant we had to reboot the entire system after a compute node failure just to reset the routes, to reroute around that single node that failed. So this shows how we over time learn what's going on these systems and then feed that back to the vendor. And the next generation, we never had that problem again because the vendor thought about it. Sorry?
Said once the systems change in the next generation, a new set of problems arise.
Yeah.
So it's a constant catch-up game that we seem to be playing. Right?
Exactly, it's a constant struggle, right? So, and a number of things like ECC, we fully understand, and that's actually less of a problem. People think that most of the bit flips actually are in the even still today, the vast majority of people thinks that the bit flips in memory are the biggest problem. They're actually not. The bit flips typically happen in the decoding logic of ECC or in the bus when basically the data gets transferred to the processor, right?
We can have the time maybe for one more question. Yeah.
Thanks for your talk. I was curious about, you mentioned lessons learned about temporal and spatial locality. And as far as I understand, this also involves users, right? How they develop their codes and how they access or use temporal and spatial locality. Maybe can you just summarize quickly what the lessons learned were in that case?
So when we look at temporal and spatial locality, we mean of errors and failures, right? And sometimes it is the case, as it was in Titan, where an application would heat up a certain part of the machine because they're using just the GPU so massively. And then you would run into overheating problems that then create all kinds of problems within the GPU. So one of the last year's mascots and this year's DSN paper was actually about the correlation between power consumption, heat production, and the increased soft error rate on GPUs. We actually do see bit flips in GPUs just because the GPU is too hot, right? So that's, for instance, one correlation we see. And that has a certain spatial but also temporal component to it, right? But we cannot then now go to the application person and say, yeah, just distribute your application, right? Because that just means that you're now basically at compute nodes that are far away from each other. And now you're paying the performance penalty for that. So what we want to do is provide the feedback to mostly the system designers to design the systems better. And then fill out all the different individual voids that are still there with maybe system software, maybe programming models that allow then to hide things. So for instance, one aspect, which I didn't talk about in this talk because it's still a little bit an iffy problem, is that we saw a lot of GPU failures on Titan. On Summit, right now, we don't even look at the failures because the system is just operational, but Summit has 50% more GPUs. What if we see a significant amount of GPU failures in Summit? How does that impact applications? We have 6 GPUs per node. If you see a single GPU failure, we basically lose 6 GPUs maybe at the same time. We have no programming model right now to deal with that. We're basically falling back to checkpoint restart. And losing a job because 1 out of 27,000 GPUs failed is not really a good programming model.